So good morning students. So this is our second experiment regarding design of PBA and PID controller. Okay, the basic aim of this experiment is to design and study the properties of proportional, integral and derivative controllers what you have studied in control system as compensators. Okay, the basic purpose of doing this experiment is that the performance of a physical system is not always good enough for a given application. In such situations, the characteristic of the system need to be modified. So this is usually referred to as the compensation design. Okay, there are standard procedures available for compensation includes time and frequency domain designs of a variety of compensation networks. Such design methods have been successfully used in many practical dynamic control systems that we have seen in many practical applications. The performance of the system is evaluated in terms of a set of performance specification. Example, rise time, peak time, settling time, peak overshoot, like that, what you have seen in control systems. Okay, so in order to increase the stability system, we need to go for controllers. So here in this topic, we are having three controllers, P, PA and PID controller. And we are going to realize this with the help of a kit. Okay. Generally, the proportional controllers, by adjusting the gain of proportional controller, the speed of response increases, but it will not create much response to the stability system. When we are going for integral gain, when we are changing the integral gain Ki, then it will decrease the speed of response, but still it will increase the stability system. When we are using differential gain, then finally it will increase the speed of response as well as the stability system. So it is better to go for PID controller rather than PBA controllers. So it will systematically reduce the steady state error as well as maintains the peak overshoot value. Okay, so this is how the experiment is going to done, and here we are having the kit for this experiment. So in this experiment, here there is a square wave generator point, or we can also use a triangle generator point. So this is given to the input of the circuit, and there are three knobs to adjust different controllers, that is KP, K and KD. So to adjust the gains, there are three knobs are there. So the standard value here, it is mentioned as, you can see that the 1 is represented here, 3 is represented here, and 6 is represented here. Okay, so here the standard value is given by the manufacturers: 1 rotation with the value of 20, and 3 rotation with the value of 40 for Ki, and for 6 rotation with the value of 40 for differential gain. And the combination of these three values, it gives us a better stabilized output. Okay, and there are 3 points at the output of the controllers. It is given to the next point. There is a summer circuit. The output of summer is given to the delay circuit, and it is connected in series to the time constant. So the time constant output is given to the amplifier, and the amplified error is given as input to my amplified value is given as input to my this differential part. Okay, this differential part, and the difference between the input and that particular output, it gives the error. The value can be adjusted till that the error reaches 0. That is the basic concept of KPI, KP, K and KD gains adjustment. Okay, so now let us do this experiment. That is, I have set KP, KD as I said earlier as 1 rotation 20 points, 3 rotation 40 points, and 6 rotation 40 points as mentioned by the manufacturer. So for this single order system, I'm going to calculate the peak overshoot value that through that by connecting the output to a CRO. Okay, so the CRO output is taken here. It is connected to channel 1. Channel 1 output is taken here. So it is connected to, one point is connected to the input, and the another point is connected to ground. So that this is measured. The output is measured in an CRO. So here you can see the waveform. So here there is an oscillation because of the continuous change in the input between these 2 points in the CRO, that is this peak and this peak. You can measure and value y, which is the peak value of this waveform, and between these two lines you can measure in value x, and with the help of the y and x value you can measure the peak percent overshoot or peak overshoot percentage as y minus x divided by x into 100%. So you need to note down the scales. Note down the scales in this. So it is 0.5 volt each scale for 2 volt, that is for 4 boxes here, and the frequency is set as 2 kilohertz, and for that you will be getting this waveform, and for this waveform you need to plot this waveform in a graph and measure the value of y and x so as to calculate peak overshoot value. Okay. Now if I am going to change the input from square wave to triangle wave, let me change the input from square wave to triangle wave. Now my waveform, the plot, it gets changed, and my peak overshoot value, you can observe that there is a change in peak overshoot. Okay, this is how the experiment need to done. You need to plot this curve and calculate the value of peak overshoot percentage. Okay, so if you are adjusting the value of gains, you can log here. If you are adjusting the values of gains Kp, Ka and Kd, then you can see that if I am adjusting the value of Kp, K and Kd, there isn't change occurring in the waveform also. You can see that if I am adjusting the value of Ki, you can see there is a change in the steady state response. Similarly, if I am adjusting the value of Kd, also, you can see that there is a change in the waveform. Okay. So by changing the gains, you can get different outputs. So in real time, the gain is adjusted during runtime till the required output reaches. That is without any error. Till the required output reaches, the gain is adjusted. That is what we need to done in the real time. So apart from this, so in recent days, PID controllers, they are used to realize soft computing techniques also. Okay. So this is all about the experiment. Design of PPI and PID controller. Thank you.